So, welcome to the next BIOCTANE webinar. I'm really honored, and it's my pleasure to welcome you here this afternoon for this exciting webinar. I'm really looking forward to dive deeper with all of you into today's topic, which you might have heard will be the conversion of acetoin and 2,3-butanediol towards jet fuel. So more or less, if you have the entire BIOCTANE process in mind, the later conversion steps. So certainly also interesting and important ones, because in the end, the fuel needs to fulfill the fuel specifications. So how do we get there? For that question, we have two experts on board today, which is on the one hand, Adriana Sousa from IMDEA Energy. She is working within the BIOCTANE project on the conversion of acet just making sure. Um, she works on the conversion of 2,3-butanediol. I felt like that doesn't really make sense into jet fuel. And then we have Gabriel Morales. He is a full professor at Juan Rey Carlos University in Madrid. He is then working on the conversion of acetoin towards jet fuels. And this is also more or less the center of gravity of both of these presentations. Before we start, I have two small organizational notes I would like to share with you. The first is about questions. After both presentations or in the end of the webinar, there will be time to discuss any questions that arise during the webinar. So if you have any questions, feel free to post them either in the chat, or there is also a Q&A function that you're free to use. And in case you would like to have a certificate of participation for this webinar, you can send an email to info@bioctane.eu. I will also post that email in the chat, so you can just copy paste it from there. And having said that, without further ado, Adriana, the stage is yours.
Thank you, Gunnar, for the presentation. I will share my screen. And it's okay now. So yes. Let's start. So first of all, I just would like to tell you that this webinar will be presented by Patricia Pizarro. That's also the coordinator of the BIOCTANE project. And however, Patricia is a little sick and he has lost her voice. So I will try to do my best to replace her in this webinar. As Gunnar said, I am Adriana Sousa, and I am a postdoctoral researcher at IMDEA Energy. And my activities at the center are mainly related to the BIOCTANE project. First, I would like to talk a little about the general objective of the project, which was detailed by Patricia and also by Gabriel in the first webinar, but I will give you a brief summary for those of you who were not able to attend to the first webinar. In summary, the main objective of the BIOCTANE project is the development and optimization of an innovative process for the production of sustainable aviation fuels from organic waste using a synergetic integration of biotechnological and the thermochemical processes. And as you can see here in the first step, in the biotechnological process, the organic waste would be converted into two platforms molecules, butanediol and acetoin, which would then be converted into jet fuel range hydrocarbons by a catalytic process. In addition, the solid waste that is generated in the biotechnological process, this solid will also be valorized through a gasification process, improving the overall efficiency of the project. To do all these tasks, the project was structured into different work packages that you can see in this another picture. in this webinar, I'm going to talk about the work packet 3, which refers to the chemical conversion of butanediol and acetoin to jet fuel range hydrocarbons. Yeah. So in the first, in these work packets, 2 groups are working, and I'm working in IMDEA Energy in the first approach, that is the integrated conversion of butanediol in the jet fuel. And another approach is the integrated conversion of acetoin into jet fuel. And this approach Gabriel will talk a little more about this second approach later. And we have in common these 2 approaches, the conversion of these platforms molecules in the jet fuel range hydrocarbons. We have some common challenges, such as we have to simplify the process by integrate catalytic stages in a single reactor. And we also have to develop active, selective, and stable multifunctional catalysts to perform these 2 reactions. So as I said, the first approach is performed in IMDEA Energy, and I will talk more about it. To address the first approach, we subdivided this general stage in 3 tasks. The first task, as you can see here, refers to the hydration and oligomerization of butanediol into C6 olefins compatible with jet fuels. And to do that, we have to optimize the catalyst used and also the reaction conditions. And I would like to highlight that these 2 reactions, the hydration and the oligomerization, must be carried out in a single step, in a single reactor. And to do that, first, we are using a model compound, just butanediol. Then, in the second task, we would use a real feedstock provided by the Hamburg University, that is another partners of the project, that performs the biotechnological step of the project. And in this stage, we have to evaluate the effect of the impurities that these effluents may contain, such as water or other side products generated in this biotechnological process. And since these impurities could affect the results that we obtain in the first task, we will possibly need to do some adaptations to the catalyst and also to the reaction conditions to overcome these difficulties of the use of these real feedstocks. And in the last task, we would already have the olefins that you need, and we have to hydrogenate them to obtain a biojet. This task is more common, and we use in the catalyst and the reaction conditions that are generally used for this process, including nickel catalyst. And I'm also presented here the targets that we have obtained, and a carbon yield higher than 70% in the biojet. So, talking a little more about the first task, this is perform the dehydration and oligomerization in just one step in a single reactor. As you can see here, generally, the dehydration reactions are carried out at low pressures and high temperatures, while the oligomerization reactions are generally carried out at low temperature and high pressures. And the catalyst used in both processes should present some acidity, And we also need to add some metals to perform hydrogenation or the oligomerization. As common properties of these catalysts, both catalysts should have a high porosity and they also high surface area to favor the dispersion of the metals that we are adding in the catalyst and to favor also the accessibility of the reactants to the active phase. So as you can see here, the main problem is that the different reaction conditions and the type of the catalyst makes it difficult to carry out these two reactions in a single step, because the conditions are not the same, and also the catalysts common used in these reactions are not the same. So how we can solve this problem? So we are evaluating two options to solve these problems. The first one that we are working now is the use of tandem bifunctional catalysts. In the first stage, we are trying to find a catalyst in the conditions that maximize the conversion of butanediol and the production of C4 olefins. And in the second stage, we are trying to tailor and couple a second catalyst bed to oligomerize these olefins. So we are trying to perform this, the conversion of butanediol to C6 olefins in one reactor, but using two catalyst beds. In the first one, we are trying to obtain butanes, and these butanes will be oligomerized in the second catalyst bed, to obtain these olefins. Another options that we can evaluate in the future or in the next steps, maybe we can use a multifunctional catalyst with these both methods and using the same catalyst support to try to obtain the same results that we are obtaining using a double bed of catalysts. So we put aquí some reactions that we have to consider to perform this first stage. So as you can see here, we can obtain butanes by producing first butadiene, but this first route that we can see here is a little bit more complicated to perform it due to the reaction conditions, are more restrictive. So we are mainly working in these two, the second and the third reaction pathways. That is the production of methylpropanol and also butanone. And after that, we need a metal to hydrogenate this intermediate compound to produce methylpropanol or also or butanol. And after that, we perform the second dehydration to obtain these butanes. And we are trying to avoid these another two pathways that we are produce some butanones or butadiene that are not our target product. So to do that, we perform some catalyst design, evaluating the amount of copper of the catalyst and also the incorporation, the different incorporation methods of to add this copper in the catalyst. And we also evaluate the effect of the acidicities using materials with different acidity. And we also tested some different reaction conditions, including pressure, temperature, and also residence time of this butanediol in the reactor. And also we evaluate the effect of add some inert gas or using hydrogen, because as you can see here, we need a metal and we also need hydrogen to perform this hydrogenation to be able to perform the second dehydration of these intermediate compounds to obtain the butanes. So what we have done so far, as you can see here, we have tested 3 different impregnation methods. And as you can see in these 10 images, the last one was the incorporation methods that give us the better dispersion of this metal, of this copper catalyst. As you can see here, this is a very big particle of copper in the first and second methods. And with this another method, the dispersion is, the catalyst is very high. And also we can see here our reaction setup. We're using a pump to feed the butanediol in the reactor. And we also have 2 connections of nitrogen or hydrogen that we can use together, or just one of them in the reactions. Then we condense the liquid products and to analyze the products. Sorry. We have to analyze the gas composition by micro-GC, and the oil composition we are using GCMS. And also, as we have some deposition, the coke deposition in the catalyst, we also have to perform some thermogravimetric analysis to quantify the amount of coke in these catalysts after use it. And we also measure the water content by Carl Fisher measurements. So just to show you some results, as you can see here, the impregnation methods have a very big effect on the conversion of butanediol. As you can see, the method that obtain that give us the better dispersion also provide us a higher conversion of butanediol, and with these other 2 methods, the conversion decrease with the time on stream. So the last method was the best one because the metal particles are smaller and the dispersion are very high, and also the conversion is stable with the time of reaction. And here we can see some composition of the liquid and the gas phase with the time. The blue bar is the water. And as you can see with the last method, we obtain a higher amount of water. So this indicates that we are having more dehydration, and this also confirms the high yield of butanes obtained with this incorporation method. The red bar. We also evaluate the effect of the support acidity using a support with lower acidity than the previous one. The acidity one is the same graphic that I presented before, and the acidity 2 is we use it catalyst with lower acidity, but using the same impregnation methods. And as you can see here, we obtain a very high amount of butanes in the gas phase and higher amount of water. That's what we are trying to do. And the next steps is the incorporation of a second bed, because we are obtaining almost all the butanes that we can obtain because we have a full conversion. And that's all from my side.
Thank you very much, Adriana.
Thank you.
That was very interesting. I noted some questions already, but we'll save them for later on. So next presentation will be Gabriel on the conversion of acetoin to jet fuels. The stage is yours.
Okay, thank you, Una. Good afternoon to everyone. I'm going to share my screen. Is everything okay?
It looks great.
Okay. So we are going to start. I'm going to present, as Adriane and Gunnar said before, the conversion, in this case, of another different molecule coming from the bioctane, which is acetoin. I will follow this index here. First of all, what is acetoin? We are going to present the molecule. How can we make jet fuel from acetoin? The strategy is something similar to what the people in IMDEA is doing with butanediol, but with some differences. And the chemical rules and catalyst requirements we need to focus on. And finally, just to present the proposal we have tried to achieve in the bioctane project at the end of the project. So moving on, what is acetoin? Acetoin is a platform molecule produced in our project in bioctane biologically. Is actually this molecule here you have is 3-hydroxybutanone. Obviously, we have two functionalities here: the hydroxyl group here and the keto group in the next carbon. So it's highly reactive molecule. It can proceed using different reaction pathways to many different products. So that will be one of the main topics here in my talk, is just to focus on the selectivity of the reactions because of the high reactivity of this molecule. Some relevant physical properties is a colorless liquid like water, similar density also, low melting point, high boiling point. Is not adequate as a fuel itself, but we can transform it into a fuel. That is our objective. As you know, it's a natural product from fermentation in yeast. Actually, is currently being produced in industrial scale through biotechnological production in fermenters, following complex, or more or less complex, metabolic routes, starting from glucose and different monosaccharides. We can obtain acetoin via pyruvate and acetoin via acetolactate. In the second route, you have here is an intermediate in the production of 2,3-butanediol. So that's why we are analyzing both molecules in this project, because they can be produced at the same time, preferentially one over the other, but we have both of them at the same time. And the typical uses right now in the market for this kind of molecule is in the food industry as flavoring for many different applications in food. Also in cosmetics, agricultural, and other chemical sectors, but in small amounts. And for sure, not as fuel precursor as we intend to do in this project. Not so far, at least, as far as I know. Next, how can we make jet fuel from acetoin? Acetoin is this molecule, remember, hydroxyl group, keto group. This is not jet fuel, of course. The typical jet fuel, as you can see in this summarizing figure, is composed of different hydrocarbons, alkanes, cycloalkanes, isoalkanes, and aromatics also in different proportions, depending on the specification of the fuel. Of course, there is no oxygen in these molecules. They are oxygen-free hydrocarbons. Mainly in the range of 9 to 14 carbon atoms, as you can see here, and mostly alkanes. And we need to transform acetoin in something like this. Of course, for doing that, we need to get larger carbon chains. Acetoin only has 4 carbons, so we need to at least reach the number of 9. And also we need to remove the oxygen. Oxygen is not an interesting atom in fuels in general, but especially in jet fuel. So the chemical strategy here, the proposed chemical strategy in our project is first enlarge the carbon chains by CC coupling reactions to get larger molecules, and then hydrodeoxygenate, or as we also say HDO, apply HDO processes to remove the non-desired oxygenated moieties, I mean ketones, aldehydes, alcohols, and so on. Any oxygen needs to be removed. This implies that I control the reaction pathway because the high reactivity of the molecule and the intermediates during the process make that the selectivity is a key point here. There are many routes, chemical routes, and many side reactions, and we have to focus in the selected ones. And that's a role for the catalyst we are going to use. So the first reaction step is then enlarge the molecule, the CC coupling, to extend the carbon chain length. Of course, we start from 4 carbon atoms, and we need to go up to 9 or 14, between 9 and 14. So we need additional molecules. And we propose to use platform molecules fulfilling the requirements of SAF production. We are not just producing jet fuel, but renewable jet fuel and sustainable jet fuel, which is called SAF, a sustainable aviation fuel. That means not everything that is renewable can be considered sustainable. We have to combine both of them at the same time. Also, we are making fuel, so it needs to be something abundant and economic, and of course, that can react with acetoin to achieve the final product. There are not many candidates that fulfill all the three conditions, and one of them, of course, is the lignocellulosic biomass. Lignocellulosic biomass, especially the platform molecules we can obtain from converting lignocellulosic biomass, specifically the cellulosic fraction, cellulose and hemicellulose, into furanic compounds. These furanic compounds fulfill these three conditions up here. So they are good candidates to combine with acetoin. Indeed, in a pioneering work several years ago, from 2016, this group published the conversion of acetoin with furanic compounds using different chemistries, and you can see here hydroxyalkylation, adult condensation, to get adult larger molecules, but oxygenated molecules. Of course, this is not jet fuel yet. We need to remove the oxygen, as you remember, using HDO processes to obtain the final alkanes that can be fully compatible with current jet fuel formulation. Analyzing these results from our experience also, the preferred routes are going to be the use of furfural here via adult condensation and the use of 2-methylfuran, this one here, using this route. Why? Because these two are abundant and cheap, and the reaction is more easy to perform. Indeed, these furanics come from the biomass residues, like this one, straw, which is hemicellulose rich. We have a lot of cellulose, and we can, via acid hydrolysis, obtain large amounts of furfural. Furfural is already a commodity in the chemical industry, so it's a good starting point to combine with acetoin. Furfural can be hydrogenated to obtain the furfuryl alcohol here to reduce this carbonyl here to the corresponding alcohol. And finally, in a second step, hydrogenolysis step, changing the catalyst, we can get to the 2-methylfuran. So furfural and methylfuran are, for us, almost the same, because they come from the same biomass. But the reaction with acetoin are different. The reaction with acetoin for furfural and 2-methylfuran is different. Here we are taking advantage of the carbonyl groups, and here the mechanism is different. With furfural, we need an adult condensation reaction, preferentially catalyzed by basis catalyst. And in this case, we go for the other route. The other route is the hydroxyalkylation and alkylation HAA reaction transformation, which is catalyzed by acid catalyst. So depending on the molecule we are going to use to combine with acetoin, we need to move to different kind of catalyst. Starting for the first one is the adult condensation with furfural under base catalysis. This will be a simplified reaction scheme where acetoin and furfural react to obtain an aldol adduct with oxygen, which rapidly evolves through dehydration to obtain this one. Both of them, these two molecules, can be used in a second step later, HDO reaction to obtain the jet fuel. This reaction is acetoin and furfural high boiling point compound, so we can do it in liquid phase, high temperature, using different kind of reactors under pressure, or even in glass reactor because the pressure is not too high here. And using base catalyst, we have started analyzing and designing special hydrotrasides, which is this kind of catalyst with acid and base properties, combining magnesium and aluminum sites and modifying it by dehydration and refrigeration, control of the amount of magnesium and aluminum, so we can achieve the best catalyst for performing this kind of reaction. So far, the selectivity is very good. That's a good point, because sulfur and acetoin are very reactive and they have a lot of side reaction, and we can control that. But so far, the activity is low. We need very long reaction times to achieve interesting conversions. So the results in this route are so far not very good. In the other part of the second alternative is the hydroxide acylation with the other molecule to methylfuran. Here we need an acid catalyst that activates the acetoin and react with the methylfuran to obtain one compound. This first compound is 9 carbons. A second compound, because this is a chain reactions, this intermediate can react with another methylfuran in the medium, so also activated with the acid catalyst and obtain this compound B. We have named them A, B, and C, as you can see, depending on the size of the molecule. The first one is 1 acetoin, 1 methylfuran, 1 acetoin, 2 methylfurans for the second compound, and the third compound is 1 acetoin, 3 methylfurans. Of course, the first two would be okay as precursor for jet fuel because of the number of carbons, but the third one is too large. We don't want to achieve this point of the reaction. So we have to control the selectivity again of the reaction. What kind of catalyst do we need for this transformation? Bronsted acid catalyst. We have started to use the most available and commercial materials with this property. We have the sulfonic acid resins like this one here, the Amberley's trademark, which are based in polystyrene little spheres and beads, functionalized with the sulfonic acid groups. And they work very, very well. The acetoin conversion is much larger than in the other route with furfural. We have good selectivity to this compound, is the one that we obtain in larger amounts. And the utilization of the second molecule, the one coming from the biomass, the methylfuran is good. We don't lose too much methylfuran in other side reactions. So the results are promising through this route. We have made some experiments of trying to optimize the reaction conditions just to focus in the production of this compound, the compound B. Remember the one with 14 carbons. This is just two representation of experimental design in order to improve the reaction conditions, the ratio of reactants, methylfuran acetoin, the temperature, but also the time and the catalyst loading. After this study, we can optimize the reaction conditions. These values we are seeing here in the slide. Just a reactants molar ratio of 2.5, 20% catalyst loading, temperature moderate or low, 60 degrees, and reaction times in 6 hours. And in those conditions, we can achieve 80% conversion of acetoin with over 80% selectivity to compound B. That means roughly over 70% yield of this compound, which is within the target of the project. Is good. The results are really good, and we are trying now to use a different modified catalyst, not just the commercial resins or the catalyst based in the same sulfonic groups, to improve these values. And after this is just to increase the chain length of the molecule. But remember, we have to remove also the oxygen in the molecule. We have to go later, not yet. The project is still running. In a second reaction step, we have to remove HDO via hydrodeoxygenation HDO of the former aldehydes. Something to take into account. This step implies always a loss of mass yield because we are removing oxygen from the molecule. So if we go, it doesn't matter the route. We can go with furfural or with methylfuran. We obtain oxygenated precursors, but when we apply this second reaction, the HDO, of course, we are losing some mass because we are removing the oxygens. You can see here the molecular weight of these compounds and the molecular weight of the corresponding alkanes final products. And there is a mass loss over 80% here and over 26%. So even with a 100 carbon yield, if we don't lose any carbon, but we lose oxygen, of course, our product is in mass less than the reactants. And the main objectives here to achieve are, of course, remove all the functions and the functionalities we don't want in the molecule, which are insaturations, carbon moieties, hydroxy moieties, the ring opening of the furanic rings and hydrolysis. We have to convert this into this. It's not only one reaction, as you can see, there are many reactions. And of course, avoiding carbon losses. We don't want to break carbon-carbon bonds. How can we do? Of course, that's just to obtain a product that is fully compatible with current jet fuel formulations, at least with the alkane part. The chemical route, of course, is not just one reaction, it's a cascade of reactions by itself. The second step is a combination of several reactions, including hydrogenations, hydrolysis, dehydrations, all of them sequential steps. And we are performing all of them over the same catalyst. So we need multifunction catalyst for achieving this goal. So the catalyst requirements in this second step will be, of course, the presence of metal active sites for the reductions, hydrogenation and hydrogenolysis part of the reaction, but also active sites. We need some acidity for the ring opening and especially for the hydration, the removal of oxygen in form of water from the system. And they need to be on the same material, on the same catalyst, so we have to optimize the balance to achieve, if possible, a synergetic effect between metal and acid sites. Of course, the material needs to have some water tolerance because there are water molecules production during the reaction, and also the pressure. We are using hydrogen for the hydrogenation part, so we need high pressure and high temperature. The catalyst need to withstand this kind of reaction conditions. So the possibilities, some of these cartoon are just to use supports with half the acidity enough and modify them with the metal part to obtain the precursor, the final fluid, sorry, from the precursor. The active metals, we can go for noble metals, platinum, palladium, ruthenium, but of course they are expensive. But we can also try to use less active materials, but much more economic, like nickel or copper, like the other, like Adriana told us before, or other similar materials. And the active supports, we need a support for this metal, but also some acidity. The classic acetolites could be a perfect candidate, aluminas, or mixed sites, including niobium or other materials, zirconia with sulfate groups, sulfate zirconia, and so on. There are several possibilities, and we can explore all of them, or at least part of them, to achieve good results. Also, it's important, it's not only the active metals and the active supports that we need to check, but also the way we produce the catalyst. How we incorporate these metals on these supports. The synthesis procedure strongly have a strong impact on the catalyst properties. There is a catalyst engineering part of the project. And finally, the biotech, the proposal within the project is not just perform one step and two steps, but get a one-pot integrated conversion of acetoin into jet fuel. That means that following the same picture that you have seen before, we start with acetoin from the working package for the biotechnological part of the project. We obtain this compound. We add some molecules, like furanic compounds, for the cis coupling, and then we obtain the oxygenated intermediates that need to be hydrodeoxygenated to obtain the jet fuel. well, the challenge is to perform all of this, the CC coupling and the H0 in one pot system, in the same reactor over the same catalyst. Obviously, the benefits from this are the simplified and intensified processes, of course, reduction in cost and operation cost, because there are no separation between steps, and you can avoid a reduction in operation costs, as I said, but also in capital costs, investment of equipment. So it would be interesting from an industrial or process point of view. But that would be something like this, having one reactor, probably because it's liquid phase, a continuous stirred tank reactor, where we add the reactants, acetoin, and in this case, methylfuran, also the hydrogen necessary for the second step, at the temperature and pressure necessary with the catalyst feed ratio. This should be optimized. And obviously here the key part is the design of a multifunctional catalyst able to perform not only the CC coupling but also the HDO. But then finally the alkanes. It's a challenge here. It's one of the most difficult parts of the project, but we are going to try, of course. We have to take into account that the reaction conditions, since we are performing everything in the same pot, we need to have compatible reaction conditions, the temperature, and the pressure, the atmosphere with hydrogen, for example, need to be compatible. We have to check that. And of course, maybe the catalysts that are best for CC coupling or best for HDO are not the optimal for the combination of both processes. So we have to think about optimizing this catalyst for a one-pot system. That will be the redesign of catalyst. But what if it doesn't work? This is research. Probably we have some problems. We have proposed an alternative to try to perform this reaction, which is the use of sequential reaction steps, which is the same reactor. It would be a one-pot reactor, a one-pot system, only one reactor, but modifying the conditions. Modifying probably at the beginning low temperature and with a temperature profile, increasing temperature profile, or at the beginning without hydrogen and then add the hydrogen. That would be interesting things to analyze. And if it still doesn't work, we can go to two sequential catalytic reactors, probably in fissile bed mode, liquid phase, but fissile bed catalytic reactors, so we can use two catalysts in connection, sequentially. That would be a partial solution. And that would be all from my side. Take-home messages from this part of the talk. Acetoin is a platform molecule that can be converted into jet fuel, sustainable aviation fuels, as we say in the project. The process implies several cascade chemical reactions, including also auxiliary material. It's not just acetoin. We need another biomass molecules like furfural or methylfuran, and also hydrogen. And finally, the selectivity is a crucial parameter because we have too many reactions, cycle reaction, and we have to control the selectivity to achieve good yields to our products. So the use of specifically designed catalysts is mandatory, and not only the catalyst, but also the reactor configuration. And that would be all from my side. Thank you for your attention.
Thank you very much, Gabriel. That was, again, quite interesting. And I have quite a few questions, but some, or at least one question also showed up in the Q&A section. So I'd like to start with that, and it addresses Adriana. So there was one catalyst, as far as I understood, with a lower acidity, which led to more dehydration. Could you elaborate on that a bit, please?
Yeah, we observed that when you have a high acidity, we mainly produce butanol, that is a very stable compound. So when we produce just this compound with this high acidity, we are not able to perform the hydrogenation and the hydration that we needed to obtain the butanes. So lowering this acidity, we are able to produce these two intermediates and perform the hydrogenation and the another dehydration. So we need acidity, but not too much. That is the question. So
Okay.
we tested different concentrations of acidity, and we observed that if we don't have acidity, of course, we cannot dehydrate the butanediol. But when we have too much, we cannot obtain all the butanes that we needed.
So a walk on a fine line.
Yeah, it's a
Finding just
balance.
the right formulas. Okay, interesting. On a broader level, I was wondering, both of you mentioned that you were working on having one process or more two sub-processes within one pot. What reasons do you have, or why do you say it's more advantage to use a one-pot process with all the complexity and the walks on fine lines that comes along with that instead of simply having two reactors?
Yeah, of course, it's more efficiency. We don't need to separate or extract some of the compounds that we are producing. It just, you put butanediol and have olefins. That is the objective. Because in separate steps are common and is usual in the literature. So it's easy. We can obtain just butanone or another intermediate compound, and after that perform another dehydration and obtain butanes, and these butanes be oligomerized in another reactor with another conditions. But of course, to do that, we need to separate these side products to obtain just the butane. So their general efficiency, the overall efficiency of the process is not the same. If we can obtain just in the olefins in one pot using the same reactor, same reaction conditions, the same catalyst.
Yeah, I would say the same. Is you can get more efficient, but it's difficult. Also, researchers like to complicate their lives, as you know. So that's what we are doing, because probably it would be easier and the result very similar. But in principle, if we can reduce the number of steps, the reaction step and separation steps in a process, of course, that would be more economical, more efficient from an economic point of view, the process, in terms of energy consumption or, and so on, materials. So, but we need to keep the same level of conversion and yields to the products. If not, there is no point.
Interesting. So more or less, it wouldn't be much research if you would just separate it and do the usual thing with step-by-step processes.
Sorry.
No, I'm referring back to what Adriana just said like a minute ago, where she mentioned that step-by-step processes are already well established, so there wouldn't be much to do research on that instead of having a new approach with several processes in one pot.
Yeah, maybe in the part of IMDEA of Adriana, yeah, it's like that, but in the part of acetoin, there are no processes established at all. So we are just
right.
in a new way.
You mentioned that it's like the first approach towards using acetoin as a platform molecule for fuel. So
industrially, for sure. And in literature, we have only found one or two articles leading with this. So it's very innovative or very difficult, or both things.
Okay, interesting. Yeah. There's another question from the audience. So now we're having those two more or less separate streams, and are you planning on merging them so that you make stuff from a mixture of acetoin and 2,3-butanediol?
Not yet. That wasn't planned in the project.
Because but I think when in my case, in the case of IMDEA, when we use the real feedstock, of course, if the biotechnological process try to obtain butanediol, always have some amount of acetoin, because it's the next step. In the case of acetoin, no, because they can produce just acetoin. But butanediol, we always have butanediol with some acetoin because of that, I put some side products that acetoin or some acids or.
But for sure, that's something we have to try, at least at the level of impurities of each other, because in the case of our chemical route, the presence of the difference is a carbonyl group in acetoin versus a hydroxyl group in butanediol. And for us, it's critical the presence of that carbonyl because it's the starting point for the reaction. With butanediol, we don't have this kind of reactions. So, but it would be interesting to check it.
Okay, so maybe for the follow-up research project then. And then there was another question related to Adriana. So how do you plan to overcome the difference in pressure between the first and the second reaction when combining them in a single reactor? Are there any plans to shift the equilibrium of the second reaction in another way to lower the pressure?
Now we are using just, we are performing reactions without pressure. But of course, the oligomerization step should be better when you're using pressure. So it's the next step. We are trying to evaluate the effect of performing these reactions with a small pressure, not too much. But maybe I decrease a little bit the conversion or the production of butanes in the first step. I'm saying step, but it's not a step because it's just one pot reaction and it's just the catalyst, this two beds in the same reactor. So we have to try to obtain the better conditions. And because of that, we are not trying to do the reactions in two different reactors, because that should be more easier if we put one reactor in the conditions that we want and the another one in the another conditions, but we are trying to do that in a single step. So let's see.
Okay, interesting. Yeah, it's not like you can clearly separate both processes if they take place in the same pot.
Yeah,
obviously.
Now we are using just without pressure, and we have some yield of C6 olefins that we can use it to the biojet. So the next step is, after perform some experiments with different temperatures and different amounts of catalyst, using the best condition to evaluate the pressure effect. Maybe we can increase this carbon yield of C6 olefins.
Okay, interesting. Yeah, see. Let's see what news will come up here. Since there are so far no more questions from the audience, I would have one more. And oh no, there is one more question, so I'll just use that. Gabriel, the use of lignocellulosic biomass allows your process to be green from the feedstock and first stage of your process, but for the second stage you use hydrogen. So what plans do you have to take it from electrolyzers? Would it then be a power to X technology?
No, that's true, of course. To be completely green, to be completely safe, the final product, the hydrogen should be also green hydrogen coming from renewable. But here in our step in the laboratory, we are using just hydrogen from bottles. So we are not trying to implement also the production of hydrogen within the scope of the project.
All right. Thank you very much. Having said that, we have almost come to a close. I have one more question related to the overall project. Gabriel, at some point you mentioned the cost of catalyst, and I'm wondering whether it's in your work packages or in any other, a part assessing the cost of the jet fuel that is going to be produced from the overall BIOCTANE process.
Yeah, that's right, Gunnar. There is another working package which is being carried out by the people from Hamburg about the techno-economical analysis of the project. So we can have an idea of the final price of the product and on the cost and its energy uses and everything. So that would be another interesting output of the project.
Oh, okay, interesting. Yeah, so I'm
And
quite
we can
sure.
compare with the conventional jet fuel. That's not only to be sustainable, green, and so on, but also competitive. Because if not, there are other routes to produce SAFs. And we have to be competitive, not with the fossil fuel, but with the other routes.
With the other renewable routes, obviously. Yeah.
But
Okay, interesting. I've heard there will be a webinar at some point also about that work package, so we'll get to that at a later stage, which I would just like to use as an opportunity for our audience to mention briefly that you can follow us on social media, for example, or have a look at our website because there will be news showing up, and we also have a mailing list where we announce the dates of the webinars, etc. Okay, I've just seen there's one more seemingly small question coming in. So Gabriel, if we still have time, could you elaborate a bit on the economical feasibility then?
too soon to say anything about that. Too soon.
If you're using renewably sourced hydrogen, so for example from electrolysis, do you have any gut sense how would it take the project economics?
I wouldn't dare to say anything because, of course, right now the price of our stuff will be high for sure. But we have to analyze to improve the process, to improve the yields, to improve the scalability, and so on. But it's not going to be cheap, I guess.
Okay, yeah. So we will have to accept it as a cliffhanger to the webinar about the overall process.
But remember also that we are using waste or residue as the input for the process, so that we have that additional benefit from the point of view of the valorization of residues.
Okay, yeah. So that's economically advantageous, and so we need to see what comes out in the end. So thank you very much to both of you for the really insightful presentations and for sharing your knowledge and the expertise on the processes and on catalysts more broadly speaking with us today. I found it really interesting. And the only thing I have left so far is I would like to point out that there will be a next webinar, as already mentioned. And Adriana, you had a little hint at some point where you mentioned that this part comes from TUH8TMI from the microbioreactor, because this is going to be the topic of the next webinar, biofilms on active substrata on 20th of March. So this is when we'll see you, all of you, many of you, hopefully, again. And having said that, thank you very much. I wish you a nice afternoon and see you soon. Bye.
A pleasure.
Bye.
Bye.
Thank you.